Hello, and welcome to our short presentation on Graphene Power Amplifiers, FET Characterization and Simulations. We will start with a brief introduction to mobile standards, power amplifiers and graphene, followed by the work we have been doing. If you'd like a more in-depth explanation of any of the material we cover, please ask for a report using the emails provided. The world is more connected now than it has ever been. Nearly 60% of the global population have access to the internet, and around 45% have access to a smartphone or tablet. In 2019 alone, there were an astounding 4.7 billion 4G or LTE subscribers worldwide. Yet for a device used by so many, how many people can confidently say they know what is going on inside their phone? One of the many essential and complicated components inside nearly every smartphone is the power amplifier. This electronic device, which amplifies inbound or outbound radio frequency and microwave signals, is used for most forms of mobile communication. To understand the necessity of this, we must look at the various standards of mobile communications through the years. 2G, or more commonly known as GSM, is used to provide many services, such as text messages, picture messages, and multimedia messages. 3G is mostly used to connect devices to the internet or other networks in order to make voice and video calls, download and upload data to the internet, and browse the internet. Nowadays, 3G has been made mostly redundant by the implementation of 4G, which provides data transfer speeds 10 times faster than 3G. The main difference between these generations of communication technology is the frequency that they operate in. A higher operating frequency means more data is transferred per second, but it also means that the total distance a wave will travel is greatly reduced. Because waves lose a lot of energy while travelling over distance, the very small signals generated by a mobile phone cannot travel far before the signal becomes too weak to be picked up. By amplifying a signal, we increase the amount of energy it has, meaning the wave will be able to travel a much further distance before becoming too weak to be readable. The current technology for power amplification is based on either silicon, gallium nitride or gallium arsenide high electron mobility transistors. While these devices continue to show superior results in any competition, the emergence of research towards graphene, a so-called wonder material of the 21st century, shows promising qualities for its use as a power amplifier. Discovered in 2004 by Andrei Geim and Konstantin Novoselov, graphene is a two-dimensional hexagonal lattice of carbon atoms with a variety of fascinating properties. It is around 100 times stronger than steel, yet has a far lower density, with an incredibly high electron mobility as well. Research on graphene remains in its infancy, primarily due to difficulties in working with the material. There are still vast gaps in knowledge of the material and its characteristics. This project aimed to help plug some of these gaps whilst making use of backgated graphene field effect transistors that are manufactured in-house at the University of Plymouth. Initially, the goal was to create a graphene FET-based power amplifier. However, due to circumstances beyond our control, this was no longer possible. The project then focused on characterizing the DC and RF properties of graphene FETs and then creating a simulation that credibly represents graphene in software that could be used for future work. The manufacturing process for these graphene FETs makes use of photolithography and RF sputtering to create 25 devices on a single chip, with 4 chips manufactured at a time. CVD graphene on a highly p-doped silicon substrate is shaped into channels with the use of a mask aligner and photoresist, before gold contact pads are sputtered on top of the channels to form the FETs. The difficulty of working with graphene means yields are only at around 40%. Each chip manufactured has 3 different types of device on it: the 2-probe channel, which were not useful for our needs, the asymmetric channel, and the symmetric channel.
There are a multitude of variables to control when working with graphene. Due to the sensitivity of a 1-atom thick channel, any impurities such as dust or hair could completely ruin a device. To counter this, all measurements must be taken inside a clean room with the correct protective equipment worn. Parasitic elements such as a contact resistance between the graphene channel and probe tips can introduce large variations between measurements, so multiple measurements of each device must be taken to remove these variations. Researchers have found that the amount of time a graphene channel is exposed to air can directly affect the properties of the graphene, meaning results must be taken quickly and accurately. Failure to do so can cause results to deviate from their expected values. Each device tested would first have a drain current to drain voltage, also known as an ID/VD test, performed to assess its validity as a device, as well as to get results for the resistance and conductance of the channel. This was a simple voltage sweep along the source and drain contacts. If an ohmic graph was found, the device would then have a drain current to gate voltage, also known as an ID/VG test, performed where the voltage along the source and drain was kept constant and the gate voltage is swept to see the effect on the drain current. This test is useful to determine the Dirac point of the devices as well as to see hysteresis loops. Comparing the different devices is important, as being able to detect patterns may lead to improvements to the fabrication process that could increase the yield. By looking at our resistance comparison graphs, the graphene channels between the 3rd and 6th contact pad were on average better than the other channels. This may merit investigation if this pattern continues to emerge during further testing. Unfortunately, most of our tests, including a lot of the RF testing, was cut short due to COVID-19, so few conclusions could be made about the manufacturing process. To establish a baseline to judge the accuracy and credibility of our simulation work, we started by simulating a gold coplanar waveguide using a pre-existing design from the 2015 paper titled Transport Conductivity of Graphene at RF and Microwave Frequencies by Shakil Awan et al. Once a sufficient match had been made, we then simulated a graphene coplanar waveguide transistor from the same paper. The coplanar waveguide and graphene FET are manufactured very similarly, with the only main difference being that a gate voltage is applied to the bottom of the FET, which changes the conductance of the channel. Although a coplanar waveguide is usually used to model transmission lines and not the transistor of a power amplifier, we are able to turn the coplanar waveguide into a transistor by changing the conductivity of the graphene channel. This transistor was then put into a power amplifier circuit to get a very rough approximation for the matching network and performance. For a more detailed explanation about the work done and conclusions drawn from this project, please review our report titled Graphene FET Characterization and Power Amplifier Simulations. Thank you for listening to this short presentation on our project work. As a reminder, if you are interested and would like to know further details or read in depth about our work, please email any of the team for the report. If you have any questions on our work, please also email those to us. We would like to personally thank our supervisor, Dr. Shakil Awan, without whom this project would not have been possible. Shakil's excellent research and guidance kept us on track throughout the entire project. We would also like to thank PhD students Benjamin O'Driscoll and Theodore Bungen for their valued time and guidance in manufacturing and testing. Finally, we would like to thank all staff and technicians working at the University of Plymouth for their continued help throughout this project.